shut down a city if they could neutralize all magnetic fields. For the moment, however, this is only science fiction. But how would everyday life differ if the principles of magnetism had not been discovered? Well, for one thing, cars as we know them would not exist. There would be no electric starter, no headlights, and most important of all, no radio. There'd be no electric lights or anything else that runs on electricity from conventional generating plants. Without elevators, only the fittest would want to live above the third floor. So skyscrapers wouldn't exist. Fortunately for us, magnetism was discovered. As early as 550 BC, the Greeks knew that a naturally occurring mineral called magnetite or lodestone had a mysterious attraction for iron. They called the lodestone a magnet because it was originally found near Magnesia in Turkey. By 1050 AD, it was known that a piece of lodestone suspended in the center would gradually swivel until it pointed in a north-south direction. Soon sailors were using lodestone for navigation. Early compasses consisted of lodestone attached to a piece of wood, floating in water so that it was free to rotate. These mysterious pieces of stone advanced sea exploration as never before. But there are other developments. In 1269, the French crusader Petrus Peregrinus chiseled a sphere of lodestone. When he sprinkled iron filings on the sphere, he found that the filings arranged themselves in lines. These lines connected 2 points on the sphere, which he called poles. The lines formed by the iron filings indicate the north-south orientation of the magnetic field. So a compass placed anywhere on a lodestone sphere will align itself with the magnetic field. The magnetic field around a magnet can easily be seen by placing a piece of paper over the magnet and sprinkling iron filings on it. Gravity restricts the filings to the flat plane of the paper, and friction keeps them from moving towards the poles of the magnet. In space, however, with almost no gravitational influence, the pattern formed by the iron filings takes on a new shape. The true three-dimensional nature of the field becomes clearly evident. But without the force of friction, the iron filings quickly migrate to the poles. During the 1500s, compasses became more and more elaborate, but explorers still believed that there were huge mountains of lodestone in the Arctic, which attracted compass needles. In 1600, William Gilbert, a British scientist, concluded that the entire planet was a huge magnet with a vast magnetic field stretching between the 2 poles. But which magnetic pole should be found at the top of the globe? We know that the north pole of a compass points north. And we also know that opposite poles attract. Therefore, since the magnetic pole in the Arctic attracts the north pole of a magnet, the Arctic pole is actually a south pole. And the magnetic pole in the Antarctic, a north pole. Ever since the arbitrary naming of the poles as north and south, the poles of all other magnets have been identified accordingly. It is for this reason that the Earth's Arctic pole is considered to be the south pole of a magnet. In further experiments, Gilbert heated a magnet until it became red hot and discovered that it had lost its magnetic properties. The interior of the Earth with its molten core is extremely hot as well. So we know that it should not function as a large magnet. Yet, the magnetic poles definitely exist. One theory holds. It is the electrically conducting liquid iron core rotating relative to the mantle that provides the north-south magnetic field of the Earth. But these magnetic poles do not coincide with the geographic poles of the Earth. The geographic poles are simply the two endpoints of the axis about which the Earth rotates, and are not directly related to the magnetic poles. So, depending on where you live, the angle between true north and magnetic north may differ significantly. For instance, if you live in Eureka, in the Northwest Territories, the angle between true north and magnetic north is 98 degrees. As far as we know, Christopher Columbus was the first to detect small variations in compass readings at different locations as he sailed westward. He determined the northerly direction using the sun and stars, and then compared this to his compass direction. To his dismay, over a period of many days, the variation between the compass readings and the stars gradually changed. But fearful that his men would want to turn back, Columbus kept this knowledge to himself. The variation between magnetic north and true north is known as magnetic declination. In Toronto, the magnetic declination is 9 degrees west of north. In Churchill, Manitoba, the declination is 0 degrees, because a line passing through the magnetic pole and the geographic pole also passes through Churchill. However, the declination for a specific place does not stay constant because the location of the north and south magnetic poles is not fixed. Another significant feature of the Earth's magnetic field is its orientation to the surface of the Earth. It is only at the equator that the field is parallel to the Earth's surface. At all other locations, the field is inclined to the surface. The angle between the Earth's surface and the magnetic field is called the angle of inclination. The angle of inclination is measured with a special compass called a dip needle, which allows the needle to pivot vertically. Exactly at the magnetic poles, the field is perpendicular to the surface. Obviously, this creates a major problem when navigating in polar regions with a magnetic compass. And this is one time when knowledge of the Earth's magnetic field can have you going around in circles.